CPU that was designed from the beginning for resource efficiency, and we'll talk a little bit about that. The basic overview of the slide, why do I need it? We'll talk about 3 ways that the ZipCPU has had some modifications to it to try and make it resource efficient. And I say modifications to it, it's really modifications to more of your standard CPU. And then we'll talk about just a couple quick enhancements and then discuss what sort of performance you can expect from using it. So the whole idea starts with a little bit of a vision. And the question here is, if you wanted a CPU, why wouldn't you buy one? I mean, look, all the CPUs below, I show, you know, a Raspberry Pi, a Teens ELC, MSP430, lots of these things. All of these things are cheaper and faster than what you're going to get on an FPGA. Why would you do a SoftCore CPU on an FPGA? And so to answer that question, I think a little bit more about it. And well, you bought an FPGA because you had something you wanted to do on that FPGA that was going to be resource intensive, that was going to cost a lot of operations, that needed to be done in a very timely fashion. You had a need for an FPGA, but now you need something that's sequential logic in your massively parallel platform. So you want to put a SoftCore CPU on it. Okay, well, if that's your background, then that sort of leads to the vision of what it is you want. You want to make sure that the application you bought the FPGA for, your CPU doesn't get in the way of that there's plenty of room for it. You want to make sure that you don't have vendor lock-in. And so this is where the microblaze and the NIOS come in. Once you get a really good design with microblaze or NIOS, and then you discover that, oh wait, I want to switch vendors, you're stuck because it's not open source. It's got a bunch of proprietary features to it. So what I'm going to argue is that you need a system within a chip. You need a SoftCore CPU designed to go inside of a chip with whatever architectural mission purpose you have for that chip in that chip. The CPU, though, has to be careful that it doesn't impact the real mission of whatever that chip was purchased for. You need it small, you need it open source. So that's our vision. So I went and I did a survey of CPUs. Can everybody read this? I mean, I ended up using the smallest font to get the whole thing on there. But so I kind of highlighted some things in red. You know, is it an open architecture? Yes or no? How many instructions? You know, most of these CPUs I have up here, if you can't read them, I've got NIOS, Microblaze, the Eco32, RISC-V, OpenRISC, and Lattice Mico. And then I'll put the ZipCPU on the far right. These are reduced instruction set computers, right? With 130 some odd instructions? How did we get reduced? Or 86 instructions for NIOS, 60 for the Eco. You know, when I first started this, and Olaf and I have had this conversation, I first started this and I counted the number of instructions in the ISA for OpenRISC at well over 200, somewhere around 220. And I said, this is not simple. I need something a whole lot more simple than this. Another thing you can look at, how many special purpose registers each of these CPUs has. 6, 25, 6, 66, 65 and more, 10. I mean, you look at some of that, that's too complex for somebody who just wants a simple core. Is there just something simpler out there? And so I'll just show this as a precursor to some of where I'm going. The ISA for the ZipCPU has 26 instructions currently fully implemented in it. It has 5 bits for the opcode. So that limits you pretty much to about 32 instructions. It has, well, we'll discuss the register set in a bit. One of the other interesting things about it, it doesn't really have any interrupt vectors. It'll be fun to watch, share with you how it supports the interrupts. It only really has one special purpose register. Does not handle 8-bit or 16-bit data. That's going to be fun to discuss. And I haven't gotten my floating point unit working, so it doesn't handle floats yet. So here's the vision of what we want in a really cheap, resource-efficient CPU. I want it to be a 32-bit CPU. I want it to be pipelined, so it's going to be reasonably fast. And I want it to be Wishbone compliant. I know I already said B4. Everybody hiss at me if you'd like. And I want it to be threadable. Originally, I said I wanted it to run Linux. I'm going to take that off the slide here real quick, but we'll just say threadable. That means it has to have both a user and a supervisor mode to it. So the choices, and we're going to discuss these, we simplified the Wishbone. That's me. Simplified the instruction set, and the interrupt vectors are just going to switch modes. Let's discuss Wishbone for a moment. So this is the first unique feature discussion of the ZipCPU. If you look at all of those wires in the Wishbone B4 pipeline mode, and I know I haven't put all of them on. Sometimes people talk about a CTI indicator, a burst length, or a cycle type indicator, a burst length indicator. Those can often be wrapped up in the tags. But can we simplify any of that? Let's see if we can simplify that. So the first thing I'm going to say is let's just remove any of the things we don't need. You don't really need those tags line. You don't need that cycle type indicator. You can merge the lock and the cycle indicator together. You can force all transactions to be 32 bits. That removes the select lines. And ignore the retries. Weren't using them anyway. So we just got Wishbone simpler. The logic now with this Wishbone is a whole lot easier to deal with. Oh, we're going to do one more simplification. I didn't find anywhere in the spec where it said what strobe had to be when the cycle line was not zero, or was 0. So I'm going to make certain that if SIC is 0, strobe is 0. Okay? And rather than a don't care, that means that inside my peripheral, I no longer have to check if the cycle line is high. All I need to check is the strobe line. And so it simplifies decoding inside of every peripheral I might have. You can see here it simplifies the slave decode logic. Instead of SIC and strobe being the indicator that you have to do something, it's now just if the strobe is high. May I recommend this change to the Wishbone B4 pipeline standards body? Hi, guys. Okay. Hi, Richard.
What you implemented is actually the whole purpose of the strobe signal.
It's what?
That's the purpose for a strobe signal. Strobe is supposed to be a decode from cycle and the address bus, and you use strobe to select your actual...
So I haven't changed anything then?
You haven't.
Okay.
Except that everybody implements it differently, but you did the right thing.
I feel better now. I am vindicated. Okay, so now I got rid of everything I don't think I need. Transactions complete. When cycle line goes back to 0, the bus is idle after the last act. Something's got to count acts. It's not the peripheral. And strobe and not stall implies a transaction took place. This is simple logic to deal with. This is simple to decode. No counters necessary inside any peripherals. Most of your peripherals that I've got are just single cycle access. They never raise the stall line at all. This makes things easy. We'll come back to this. So we just simplified the Wishbone. Here's a picture of the CPU. It has 1, 2, 3, 4, 5, well, yeah, 1, 2, 3, 4, 5 stages to it. Your prefetch and cache, your decode, your read operands. Unlike a lot of RISC CPUs, I've got the arithmetic and the memory axis side by side in a pipeline. They have adjacent pipeline structures as opposed to consecutive. One of the things that makes the RISC CPU very unique is that it has not just 32 instructions or 32 registers, but the register set is split into 2 sets, each 16 bits, each mode specific. If it's in user mode, it will use the user register set. If it's in supervisor mode, it'll use the supervisor register set. One of the fascinating things about the 2 register sets is interrupts are only enabled in user mode. So the way this handles interrupts is it jumps from the user register set to the supervisor register set and back again. So the interrupt brings you to the supervisor set. When the supervisor's ready to send you back, you go back to the user set. Instructions. I said we were going to simplify our instructions. We have a 5-bit opcode. You can see that up there. There's a destination register. That's what DR stands for. Every instruction can be executed conditionally. There are 3 bits for a condition. And then your instructions can either be Let's see if this works. An operand with a condition to a register plus an immediate and put the result in register A, that's that destination, or just an immediate in a register A. A lot of the other architectures out there have registers 0 assigned to automatically be 0. And so if you want to do something with a register with 0, you have to use register 0, and then your 32 registers now drops down to 31, and some things like that. In this case, we have 1 bit that says whether or not we're going to use an 18-bit signed immediate or a 14-bit signed immediate plus a register for our instructions. This was going to be every instructions format. It worked until you needed access from the supervisor mode to the user registers, and it worked until you wanted to load a large number into a register. So we had 2 more opcode formats, 1 for moving, and then 1 for loading immediates, and we just stuff a couple things into a no-op group. Entire design here, trying to keep things simple. 32-bit, we said there was a 5-bit opcode that says you can have 32 instructions. Here they are. You can see I've still got 2 points reserved. That's 26 instructions. Actually, the floating point instructions I didn't count in the 26 instruction list because I wasn't counting them for everything else. You know, try and keep things simple at the simplest CPU out there. So 26 instructions, not including the floating point unit I don't have. A couple in red. We can come back and discuss them. Some unusual instructions. I have a bit reverse instruction. Anybody familiar with FFTs? Don't you want to do that bit reversed addressing? I put the bit reverse instruction in there specifically for that. It's now the way I load into the high bits of a register, so it's a fundamental part of the architecture now. Test is an unusual one. It's just an AND that sets conditions. Conditional compare will set the conditions only if the condition it's conditioned on is true. Does that make sense? Okay, rotate left, population count. The compiler doesn't seem to use them. Other things are pretty standard. The branch instructions just add a number to the PC. So again, I'm still sticking to the very simple format we have. Branch is nothing more than just an add like any other. You can XOR to the PC too if you want to. I don't know why you'd want to, but I kept things simple for you. Some of the things that are missing that you common in other architectures, there is no load byte, store byte, load half word, or store half word instruction. Remember I got rid of those select lines? This is one of the consequences of that. That means that every access in this CPU is a 32-bit access across the bus. Size of character is 32 bits. There's no return instruction, call instruction, add with carry, compare and branch. All some unique things. Here's the conditions the CPU supports. Not quite all of the signed conditions and only one of the 4 unsigned conditions. So that made compiler building a little bit interesting. Function calls, I mentioned there was no jump to subroutine. So how do you do a jump to subroutine? You move return labeled plus the PC to R0, and so that sets it into, move PC plus 2 into R0 and then jump. Returns are just indirect jumps to R0. Interrupts, I said interrupts were interesting. I'm sure everybody's familiar with your standard interrupt approach, where when there's an interrupt, the CPU, the decode logic automatically stuffs some extra instructions into the instruction stream. It pushes the condition codes, it pushes the PC, and then it makes a long jump to wherever this interrupt table is. Not so on the ZipCPU, okay? The ZipCPU has a different approach. Note this requires extra logic to support. We tried to get rid of a lot of that logic. ISR coding can be difficult if you tried coding ISRs from C. So let's try a different approach here. Remember I said all we do is switch register sets? So the way it works is you start in the supervisor mode upon boot up. You can set the user registers and then you can switch to the user mode from there. When an interrupt happens, you just come back to the supervisor instructions. Nothing special about this interrupt service routine. You can handle interrupts, traps, exceptions. The only unusual thing is this zip RTU, or return to user space, instruction that the compiler's been taught about. It just maps straight into an assembly instruction, which is an OR to the condition codes register. I feel like I'm talking really fast to try and get through a long briefing. Smile, everybody. This is actually some fun stuff. A couple basic enhancements. I'll chat about the pipeline memory access and the early branching. There is a 14-bit packed opcode. It's not really packed opcodes, 14-bit packed instructions, where you can pack 2 instructions into 1 word. There is that mode. That's in the backups. Some of the future things I'd like to do, memory management unit and data cache. Note, there is no data cache yet on this CPU. I've scribbled them out about 2 times on this trip and didn't bring my laptop with me, so every time I end up scribbling out so many errors in my scribbles, I can't read my scribbles anymore. We'll see what I come up with when I get home. Okay, let's talk about that Wishbone bus for a moment. Without pipelining, this is still the pipeline mode, although this might as well be the classic Wishbone mode. Cycle line is high for 2 cycles. Strobe is high for 1 cycle in the classic mode, or 1 cycle in the pipeline mode. It would be 2 cycles in the classic mode, or at least until the ACK comes back. Without doing much with pipelining, in this mode, you've got a minimum of 3 clocks per access. Okay? Well, can we do better? Suppose we can use that pipelining mode. Now I have the strobe high for every single time I want to have an access. The address and data lines are valid every time I want to have an access. And whenever the ACK comes back, I get 1 ACK for every time the strobe was high and the stall was low. I can do this best case n plus 2 transactions, or n plus 2 clocks for n transactions. That's a whole lot faster than 3n. Can we use this inside of a CPU? ZipCPU supports using this in load and store instructions. Remember I said we didn't have a data cache. So this is a little unusual. So if you have 2 instructions that are adjacent, that access adjacent pieces of memory, or access the same piece of memory, it'll automatically use the pipeline mode. So what that means is the first, here you have an example with a stack frame setup down here. You allocate some stack space. Your first store may take you a little while to get to the bus, to get to the peripheral, to go through the arbiters, however many, whatever it takes to get there. But then your next access is just 1 clock. Your next access is just 1 clock. So instead of having to suffer that difficult memory access time for every access, only the first one suffers a memory difficulty. The next several are 1 clock each. Early branching. Normally a branch would cost 6 clocks because you'd have to get all the way to the end. You flush the pipeline once you write a new value to the PC. That's kind of expensive. We picked 3 instructions and said, let's make these early branch instructions. In this case, you only have 1 missed clock. The 3 instructions are add something to the PC, load an immediate value into the PC. That's kind of limited to 23 bits, so that puts your code in a very small location of memory. Or that last one, load from the PC's address into the PC. If that looks like a really funky instruction, it's another way of saying load the next instruction word into the PC. It's a way of getting a full 32-bit address into the PC without needing any more registers. It's there because it was an afterthought, because when I built the CPU, I didn't necessarily understand how the linker had to work. It works quite well, though. It's been optimized. And you can see the first 2 take 2 clock cycles to do. The third one is just inside 3 clock cycles. And then I mentioned how the load immediate into the PC is hardly ever used. So let's talk about how it performs. Sort of the bottom line, right? How good does this thing work? I did not do this with CoreMark. Matter of fact, I cannot test this with CoreMark. I tried. CoreMark requires that bytes be 8 bits, that shorts be 16 bits, and that ints be 32 bits. And in this architecture, bytes, shorts, and ints are all 32 bits. Remember, I got rid of those select lines. There are some consequences to that. One is CoreMark. I can modify CoreMark to make it work, but then I can't call it CoreMark. So, okay, we'll use Drystone instead. It's got to be GCC compiled code to make things fair. We'll hand optimize some assembly, library routines. Everything will fit in a block RAM. We'll use an instruction cache. Remember, I didn't have any data cache, so that's going to hurt. And I put it in a Verilator simulator. This one is cycle accurate. So for anyone struggling with cycle accurate simulations, may I recommend to you Verilator? It's awesome. Just build cycle accurate CPU, peripheral simulations to talk to your core. And then for anyone trying to repeat this, the formula you can get from Wiki as well, or Wikipedia. So here's some of the performance here. In honor of our Digilant representative here, the S6 SoC. Anyone's familiar with that CMOD S6? It's like the smallest FPGA I could find that wasn't a CPLD. Has 2,400 lookup tables on it, that's it. I figured if I was really trying to build a resource-efficient CPU, it should be able to fit inside the smallest FPGA out there. At 2345 LUTs, it fits inside 2,400 just barely. Sad thing is I removed a bunch of code. It was 2,200 and I removed a bunch of code and now I get 2345. Go figure. There's some variance on this measurement of LUTs. But anyway, looking at the Zula 2 system on a chip, without a CPU, just a baseline system, just all the peripherals there, we'll start with a 2,400 LUT count, and then we'll just add things, and you can see how many LUTs were added and then how many total for the CPU along the side. There is a non-pipelined version of the CPU. I basically ripped out all the pipeline stall logic. That costs about 1,286 LUTs. You have to add the multiply before you can get your first Drystone measure at 0.128 Drystone MIPS per megahertz. Okay, if we pipeline the CPU, it more than doubles up to about 0.46. Haven't we seen better Drystone measures yet today and yesterday? Okay, well, let's go up a little higher. Put in that pipelined memory and it goes to 0.61. Wow, what an impact you have for doing that pipelined memory approach that we just talked about. Go ahead a little bit further and put in the early branching. It loses 2 LUTs on early branching. I told you there was some variation in how this LUT count is measured. I don't trust it that well, but this is what I have, so I'm presented as performance. If you put in a whole bunch of other basic peripherals, an interrupt controller, some timers, some performance counters, you get up to about 3,100, 3,700, still less than 5,000 LUTs for the CPU. Throw in the DMA. All right, is it cheating to use your DMA for the mem copy inside of Drystone? Thank you, I appreciate it. You agree with me. We'll use the DMA for that. We get up to 0.744. This is doing pretty good. OpenRISC can do better. Why? OpenRISC gets about 0.97. I went and did a bunch of work with OpenRISC. Well, the reason why OpenRISC does better is because the newlib library allows you to pack 4 characters into a 32-bit word, like, 4 8-bit bytes in a 32-bit word. That just makes sense, right? Well, the compiler doesn't naturally pack 4 characters into a 32-bit word in the ZipCPU because 32-bit accesses only. Okay, so if you modify Drystone to allow you to do packed string accesses, so it'll be fair. Oh, but wait, I just broke Drystone by modifying it. Okay, we're fair though, 0.95 to 0.97. You get comparable performance, and this without a data cache. Pretty impressive if you ask me. How do we do? Did we build a simplified instruction set, simplified bus, simplified interrupt processing, open source, low area, SoftCore CPU? Welcome to the ZipCPU. You can find it both on GitHub, and OpenCores. There are the two addresses for it. And this is the end of my talk, but just to be friendly to anybody who wants to take a picture of what that that CMOD S6 looks like, and just to see again that, yes, I did get a CPU inside there. I did run a multitasking operating system inside that using the ZipCPU, and it is a preemptive multitasking process. I figure that's kind of impressive. Any questions now that I got to the end here?
Actually, I have a question, maybe less controversial perhaps than the others. Because already on the first slide I was wondering, you were talking about very simple CPU, and the motivation is really great, I think. I really understand it. But I was wondering, why do I need FPU for that? Like, is there any use case for an FPU in a deeply embedded control core?
Learning. To learn about how to build an FPU.
Okay.
But to your point, I don't have an FPU in there, and nobody has contacted me about putting one in there or saying I need one in there. So, yeah, your question is quite valid. In case somebody wants it, I've got, instruction set space reserved for it, but don't have it yet. Sir?
Bearing in mind everything that's been said at this conference, I wonder why you chose GPL version 3, bearing in mind it's a hardware device and all the issues that have been mentioned to do with using GPL for hardware.
I'm a businessman. If anybody's interested in something other than a GPL license, come chat with me. We'll make something work for you. Okay? I understand there are issues with it. In the back, Mr. Bennett. How you doing, sir?
Thank you, Dan. This is a project after my own heart. I like really small processors. Can you just go a bit further? You've talked about how you've got rid of the lines, so you have to write whole words at a time. Does this cause you problem with memory mapped devices? The trouble is I don't know how the digital board works, but I can see if I had a UART in there, which has its nice block of byte registers, and flattening 3 others when I want to write one particular one is not going to make my UART work well.
So I have my own UART. It uses 4 registers, all 32 bits. I have actually enjoyed building peripherals with a 32-bit word configuration, access, usage to it. I found it valuable what you can do. So for example, if I want to send a packet across the network, I fill up the data for the packet and I just have to write 1 word. That does all the configuration for a network, that tells it the length of the packet, and off it goes. With the UART, there is 1 configuration word that tells you exactly what your baud rate is, exactly how many bits per stop bits you have, how many data bits you have, are you using parity, is it even or odd parity, or is it fixed parity? It all fits in a 32-bit word. It's amazing how easy it is to configure things with 32-bit words.
Yeah, that's fine. I don't deny it, but it does mean you've got to have your own version of everything.
To be honest, that isn't what's caused me problems. What's really caused me problems is that program or that library called newlib. I have not been able to finish porting it yet because it relies on uint 16s, int 16s, uint 8s, int 8s, and so on and so forth. And I think that's sort of a harbinger of things to come. That's why I don't think I will necessarily be able to get Linux to run on this, although it was originally one of my goals when I set this up, was to run Linux on it. Sure. Anything else?
Just a comment on Jeremy's question. You can just throw away the 24 high data bits as well, and you will have a 8-bit. Yeah.
And the fun thing from reading from the UART is not only do you get your 8 bits from the UART, you get a bit that says if you read and it was invalid. You get another bit that says if the UART's in a break condition. You get another bit that says if there was a frame error or a parity error along with that. And so you can very easily check if there's no high order bit set, then I got a bit or a valid read from the UART. If there are, you can dig into it and see what's up. Amazing what you can do with 32 bits. Yes, sir. Microphone.
Andre Powell, what do you have any debug capability?
Oh, I have a wonderful debug capability to this. I would love to spend another presentation on it. I think I'm out of time. One of the things I have put together is what I call a Wishbone scope. It allows you to record 32 bits on every clock, or at least every clock a particular enable line is set. You can even have it set up to record not on the same clock the Wishbone's on, so you can have an asynchronous record going on in there. I can record anything 32 bits at a time, once per clock, and then come back and read it off the Wishbone bus. I can record from inside the CPU. I can record from inside my peripherals. I can record from inside whatever I'm working with. So if you find yourself working with a peripheral that wasn't as well defined as you'd like, I just throw one of these scopes on it and I read it out after whatever trigger has happened. It will always record until a trigger takes place. Once the trigger takes place, it has a countdown. You tell it how far to count down, and then it stops recording. So if you want, for example, to detect when your CPU crashes, you could set the trigger to be, the CPU hits the halt condition, and then it will record right up until that. When you pull it off the scope, you have everything leading up to the crash. If you don't know what the condition is, but you know it happens sometime after you switch from interrupt mode to non-interrupt mode, supervisor mode to user mode, you can set every time just before you set user mode to supervisor mode to user mode, you can set the scope up to trigger now. And then when you come back again, well, obviously you hadn't crashed, trigger now again. You can do that sort of thing, works very well. I've debug quite a few things with that scope. You will find it on open cores. You're welcome to use it. It's very useful. It requires a Wishbone bus being set up and an alternative way of reading from that bus, which I've used for all of my development.